Hi, Professor.
Oh, hi, hang on. How's it going?
Good, good. How about you?
Good. What's up?
Yeah. How are you grading the first vascular activity, like on completion, right?
No, there's part of its accuracy too. So we talked about
Okay.
on the tutorial kind of what aspects make a good model.
Yeah.
So I'm looking to see if your model is relatively accurate compared to the image data.
Uh-huh.
I'm also checking just for the quality of the model too, just for like smoothness and
Oh, I
making sure
see.
the junctions are good too. Yeah.
Mhm.
Sure.
When remember last time we had to create a model, create all of them in one model, and then I tried to do that, and it showed me the warning that have the some of the blood vessel have the intercept, and then after it still allow me to create it,
Yeah.
but it don't show on the four views.
Oh, the model doesn't show up at all.
Yeah,
But does it show a list of like the
yeah,
the accounts?
yes.
That might just be a rendering issue. You may just have to refresh the view. And so when in the bottom, so I would just maximize one of the views and then it might.
Yeah,
it
I
might-
tried all the way, but
it
like
was
when I
so-
create part by part, then
Yeah.
it allow me. Because you said like we have to read how many cap they have.
Yeah. I wouldn't worry about it too much right now. That's something we could probably fix for the when you actually do the midterm project.
Okay.
The fact that it's creating the walls and the caps there
Yes.
means the model's there. It just may not be rendering.
Okay.
So I wouldn't worry about it too much.
Okay, thank you.
Yeah.
Because I tried to create all of them and then it say intercept one of the blood vessel, the
Uh-huh.
auto vessel.
Yeah.
But
You can tell which ones don't have the intercept correctly because it has an extra cap.
oh yeah.
So there's only one vessel in your model that should have two caps, which is your aorta, the first one.
Or different.
All the other ones that have two caps, you need to go back and fix it.
Yeah, so that's why, but like when I create part by part, that allow me his cap weird.
Yeah, that's weird. I think it's just rendering. I think
Yeah.
it's there. It's just not showing up.
Yeah, and then sometimes it's like when I try to create a model,
Mhm.
the software don't let me to create a model.
It just gives you an error? Or
No, it's not. It's when you click create a model,
Yeah,
it not show anything.
it just freezes.
It just freeze and then you
Okay.
have to shut down and then reopen it.
Yeah, I mean that happens sometimes because it's not the most optimized software. So
Oh, yeah, okay.
that's just.
I thought I did something wrong.
Oh, no. That's just the software.
Okay, thank you, bro.
Okay, it's 4 o'clock. Let's go and get started. All right, good afternoon, everyone. How's everyone doing today? Hanging in there? Yeah. A lot of people on Zoom. I know it's probably a busy week for you guys. I'm sure you guys have midterms and stuff like that. So, yeah. So appreciate you guys coming. Especially with the recorded lecture. Sometimes I do actually lecture to almost empty rooms. So not something I'm a stranger to. But okay. So the plan for today, we are just going to continue with our lecture notes. And so on Tuesday we introduced the concept of lump parameter modeling. And so today we're just gonna be doing all examples today. So we're gonna be doing, I think we started an example last time, so we'll finish that one up. We'll show, we'll talk about how to derive the equations for a lump parameter model. We're gonna get into a little bit of MATLAB stuff today too. And so, generally, these lump parameter models, they're governed by ODEs, and so you should be able to solve them by hand. But a lot of times it's just more convenient to use MATLAB. So, we'll talk about how to use that today. It's not a lot of coding, so don't stress out about it, but it's we're using MATLAB as a shortcut. Think of it that way. Okay. All right. So some announcements. Remember, your vascular modeling tutorial is due tomorrow night, and so make sure you get that in. So I've talked with quite a few people this week, so make sure if you don't get a chance to speak with me, get feedback. Definitely reach out to people. So I'm seeing that a lot of people are doing really well on the tutorial, so make sure you get some help from other people if you need it. Next week, remember, I'm going to open up a poll for you to choose what type of model that you want to use for your final for your midterm for the rest of the midterm project. So definitely keep an eye out for that. And I'm also planning on posting the next homework assignment as well, which has to do with this lump parameter modeling. So things are going to ramp up quite a bit for this class, and so just want to warn you guys and just kind of be prepared for it. Okay. All right, that's all my announcements for now. Are there any questions I can answer before we get started today? Okay. All right, so let's go ahead and pick up where we left off on Tuesday. Right, so remember this whole week, it's dedicated to this idea called lump parameter modeling, which we kind of discussed in detail on Tuesday. Where oftentimes when you have these kind of very complex blood vessel networks, cardiovascular networks, you want to simulate it, you want to run a model on it just so you can understand the behavior better. But if you don't want to run a full CFD, there's a lot of kind of lower order models that you can do, right? And so the simplest one that we can do is a lump parameter network, or lump parameter model, which uses circuit elements and circuit laws to simulate our blood flow. Okay. All right. So last time we talked about the three different elements that we're going to consider. So we have the resistor, we have the capacitor, and we have the inductor. And so we talked about what each one physically represents. And then where we left off was, doing an example to show how do we actually derive these equations. All right, so this is the example that we're looking at. So we have a simple RC circuit. So we have flow coming in, right? And so our inlet boundary condition on the left is Q of T. And so that represents the flow of blood coming into this network, right? At a certain point, this blood is going to split, right? And so it's going to go, some of it's going to go to the resistor, some of it's going to go to the capacitor, okay? And then once it passes through there, it's going to meet up at the end. And then, go to ground, right? So a very simple model, very simple Windkessel. And what we wanted to do in this example here was to derive the ordinary differential equations that govern its behavior. Okay. All right. But before we do that, and in fact, let me just because the learning objectives are in the way, let me go ahead and draw the vessel again down here. We have the resistance, we have the capacitance, we have the flow of blood coming in, Q of T, okay? All right. And so when you view a network like this, right, we have to think about our circuit laws, right? So the blood, in this case, is going to flow along wherever we see a circuit or a wire, okay? And so when you look at a circuit like this, it almost looks like the blood is kind of splitting into two paths, right? And so, and it seems like that because I just literally said it. And so, the blood's going to go part to the resistor and part to the capacitor, right? And so, after kind of getting to this point in the class, it almost kind of looks like the blood is going through a bifurcation, right? So we talked a lot about that when we went through Murray's law. That it happens very often in the blood, in the cardiovascular system, where the blood is going to come in, it's going to split into multiple paths, right? And so this looks very similar to that. So this looks like the blood is kind of going into a bifurcation. It's going into two daughter vessels. One daughter vessel has resistance, the other has the capacitance, right? That's actually not the case in here. Okay. And that may be kind of a trippy thing to kind of to say when obviously the blood here is going to split in between those two, right? Here, this split here kind of represents something a little bit more conceptual, a little bit more theoretical, right? So let's think about kind of a blood vessel like this, right? Right. So we know this blood vessel is a flexible tube, right? And this flexible tube is going to do a couple things. And so when blood comes in, right? So let's say we have the flow of blood coming in, Q of T, right? That blood is going to do a couple different things within the blood vessel. On the one hand, some of that blood is going to go towards inflating the vessel. Right? Because as this blood vessel inflates, its radius is going to increase, its volume is going to increase, right? So it's going to get a little bit bigger, just like this. Okay. And so whenever you have an increase in volume, that has to come from somewhere, right? And so that increase in volume comes from the blood, right? At the same time, some blood is just going to flow right through, right? Not all the blood is going to go towards inflating the vessel, right? So some will just going to flow right through, okay? And so when you look at it from this perspective, the blood in this case, does two things, right? Right. And so on the one hand, we can say that some blood's going to inflate the vessel and some will flow through, right? Let's look back at our Windcastle model here and let's kind of draw that comparison, right? Remember we talked about last time the capacitance represents the ability for a blood vessel to temporarily store blood. In other words, it captures the ability for blood vessels to inflate and deflate, right? So the flow that goes to the capacitor is it basically represents the fact that blood comes in and can inflate the vessel itself, okay? Meanwhile, the blood that flows through, right? As the blood goes through, it's going to be impeded from viscosity, right? From the friction, right? And so that's kind of the other path here. So even though this circuit, the way we drew it here has a parallel path, you know, it really just represents one vessel. And that one vessel is and the fact that we have a parallel path means that, you know, this one vessel can do multiple different types of behavior. Okay. So I wanted to make that clear just because I've noticed that, you know, last time I taught that point was a little bit confusing, that, you know, just because you see a parallel path in the circuit itself doesn't necessarily mean that there's multiple blood vessels here, right? This one kind of RC circuit right here, even though it has two paths, it just represents one vessel. It's just two behaviors for one vessel. So that's kind of the confusing things with doing lump parameter networks, because we're kind of lumping together, you know, full on physics into just one circuit. When you have a complicated situation that can exhibit multiple different types of physics, you know, you have to actually split that up into different circuits. And so this is kind of the compromise that you make. Okay. Now, if you were to see a circuit like this, okay. So this is just a theoretical example. We're not actually going to do this in the example here, right? So this right here, this would be a bifurcation. Because we have kind of multiple of these units together, right? Right. So it takes a while to get used to. And so, you know, you look at, you know, for me, you know, I've seen these for years. And so, you know, I can look at this and say this is a typical bifurcation. You have one vessel coming in and then it splits into two like this, right? But when you're kind of, you know, when you're first kind of learning this and you're kind of, you know, digging up the cobwebs in your brain about how circuits work, you know, it can be a bit confusing. So, you know, just give it a bit of time. You know, we're going to do a lot of examples in the class. The homework's going to give you a lot of practice too. And so, you know, just kind of, you know, as always, whenever you're learning something new, you know, take a bit of time, kind of talk yourself through the logic, talk yourself through how it's, you know, how it's supposed to be designed, and then start to kind of make more sense from okay. Okay, but we're not doing that one. We're just doing this just this one vessel right here. Okay, so we have this RC circuit, and what we want to do from this example here is we want to derive the ODEs, or the ordinary differential equations, that govern this circuit. Okay. All right, for all the LPN problems that we're going to do in this class, that's always step one, is to derive the equations. Okay. Okay. All right, so to derive the equations, you know, we're going to rely on the kind of the basic equations that we talked about last time. But the first step is to first of all determine how many differential equations are we going to have. Because that's an important starting point, because, you know, we say derive the equations, but, you know, oftentimes there's going to be more than one. Here, there's only one, but, in the next examples that we're going to do, there's going to be more than. Okay. All right. And so to determine how many differential equations that we'll have, it depends on how many circuit elements. In particular, it depends on how many capacitors and inductors that we have. Okay. Because if you look back to our lecture from Tuesday, each capacitor and each inductor is governed by its own differential equation. Okay. And we're going to use those governing differential equations to form our entire equation for the circuit. Okay. All right, so for this particular example, we have just one resistor, one capacitor. The resistor is going to be important. We don't have a differential equation that governs the resistor itself. But it is going to work its way into our equation, so it's going to be there. Just don't worry. But just purely the number of differential equations is based on the capacitors and inductors. Okay. And we base our whole analysis on the number of differential equations, because that's essentially what we're going to be solving for in math. Okay. All right. Any questions on this so far? All right. So once we determine the number of equations, the way that we actually solve for the equations is through the application of Kirchhoff's circuit laws. Okay. So we'll go through each of the circuit laws. There's two main ones. There's Kirchhoff's current law, and there's Kirchhoff's voltage law. So let's do the the current law first. This one you'll use pretty often in this case. And there's another name for it. So it's just because we're doing circuits, I'm going to attribute it to Kirchhoff because he's the one that discovered it. But if you want to put it in more fluid mechanics terms, Kirchhoff's current law is essentially the same thing as conservation of mass. You want to put it in electrical terms, it's conservation of charge, I guess. So conservation of mass in a flowing fluid situation means that inflow is equal to outflow. Okay. Okay. And the way that we apply Kirchhoff's current law in a circuit like this is to apply this at the junction. So whenever you have flow that's going to split into multiple paths. Okay. All right. So we have one junction in this model. Well, technically two, but we have one here that's on the left. That's the one that's more interesting. Okay. So the one on the left basically says that we have inflow coming in, Q of T, and that's going to split. So some of the flow is going to go towards the resistor, and some of it's going to go toward the capacitor. All right, so it looks like this. And so if we have kind of blow this up, right? Coming into this junction, we have Q of T, that is our inflow condition. Okay. Some of that flow is going to go to the resistor, QR, and some of that flow is going to go to the capacitor, QC. Okay. All right, and then by conservation of mass, right, we have one inflow into this junction and two outflows. We know that Q of T has to equal to QR plus QC. Right. So that's good. All right, so now that we have this equation here, this conservation of mass equation, what we're going to do is that, we're going to take the flow over the resistor and flow over the capacitor and replace these using the circuit equations that we went over last time. Okay. Because what that's going to do, because essentially, we want an equation that incorporates the value of the resistance, R, and the value of the capacitance. All right, so we want to factor those in because QR, QC right now are kind of unknowns, and so they're kind of mysterious.
This is in terms of volumetric flow rate?
Exactly. Yeah. All these Q's here represent volumetric flow rate. Yeah. All right. So let's go through each element here and see if we can get an expression for the flow over that element. Okay. Let's start with the resistor. This is the easier one to do. All right, so for the resistor, we have just one equation, right? So the resistor just has Ohm's law. Or, in our case, the fluid mechanical version of Ohm's law, right? And so if we have a resistor like this, right? If we have P1 up front, P2 on the backside, and R, okay? The flow over the resistor, QR, through Ohm's law, is just going to be P1 minus P2 divided by R. And just the pressure drop, or in other words, the voltage drop on the resistor divided by the resistance. Okay. All right. Let's put this in terms of the values that we know from the problem itself, right? And so I should have mentioned it here, but if you notice from the original drawing of a circuit, right? I've labeled the pressure at the junction between the resistance and capacitance. I've labeled that as P. So that kind of goes back all the way up here, right? And so P here is the resistance at the junction, right? And we know that every point here that's connected by wire is going to have the same pressure or the same voltage, right? And so if we follow this wire from this junction all the way to the front of the resistor here, we know that the pressure right at the inlet of the resistor is going to be the same as this junction because we're all connected by a wire. Right? All right. So that means if we were to plug this into our equation here for the resistance, right? P1 is going to be equal to P. So QR above is going to be P minus. Okay. We know the resistance of the resistor, so the resistance of the resistor is just capital R. Okay. The other thing we have to plug in is the downstream pressure, P2. Okay. So let's look at our circuit again and let's see what the pressure is downstream of the resistor. All right, so we come back to our circuit here. We know the inlet pressure here, the upstream pressure is P just because it's all connected to a wire. Okay. After the flow passes through the resistance, the flow is going to go this way, right? It's going to come out to ground. Right? Remember, whenever you see the symbol right here, the symbol essentially means ground, right? And ground is our reference point. So ground is basically where we're going to say the pressure is 0. Okay. That's always the case. So whenever you see a ground symbol in your circuit, you're going to assume that it has 0 voltage or 0 pressure. Okay. Once again, we're gonna follow this wire here. Okay. Everything that's connected by a wire has the same pressure. And if we come back up to the back end of the resistance here, we know that P2 after the resistor is going to be equal to 0 in this case. Okay. It's on the back end of the it's connected straight to ground, right? All right, so that gives us everything we need. And so if we plug in 0 for P2, this tells us that our flow over the resistor is just P divided by R. All right, any questions on that? Okay. All right, so we have our equation here for the flow over the resistor. Now let's do the flow over the capacitor. Or I should say the flow into the capacitor, a bit more accurate. Okay. So for the capacitor, we actually have a differential equation, right? So if you look back in the notes, the pressure change, the change in pressure on the capacitor it depends on the flow coming in. Okay. In mathematical terms, that statement here is derived as QC, or I should say dP dt, right? So dP dt there represents the change in pressure on the capacitor. Okay. This is equal to QC divided by the capacitance C. Okay. All right, so if we solve this equation for QC here, so I'm just going to multiply C by both sides, we get QC is equal to C dP dt. Okay. And so the flow on the capacitor, as we have it outlined there, is the capacitance multiplied by the change, the time derivative of pressure, so dP dt. Okay, so now that we have both expressions, let's go ahead and plug those back into our conservation of mass equation. Our conservation of mass equation, let me write it down here one more time. Q of T is equal to QR plus QC. Okay. If we plug in for QR and QC, what we get is P over R plus C dp dt. Okay. Right. I'm just going to do a little bit of simplifying here because usually in these differential equation type of things, we like to isolate the time. We like to isolate the time derivative. Okay. So let's divide the whole equation by c. And I'm just going to swap the places too, so that we have the time derivative on the left. And so we have dp dt plus p over rc is equal to q of t divided by c. All right, so what we have here is we have obviously a differential equation. Okay. Usually for these types of problems, R and C are just constants. So you can assume that they're known. You'll be given these values usually. Another thing that you can typically assume is that you most of the time know the inflow condition. So Q of t is some function of t, but it's also known. Okay, that's just the inflow to your model. Typically for our applications, we use a sinusoid for Q of t, just because we know we've seen before previously that the waveforms in the cardiovascular system, both the flow and pressure waveforms kind of follow this kind of repeating pattern. They're like a periodic wave. And the simplest periodic wave is either a sine or a cosine. And so for the homeworks and everything, a lot of times you're going to see me use sine or cosine for Q of t. Okay. And so what we have here then is an ordinary differential equation. And what we're going to solve from this equation is P, or the pressure on the capacitor. Okay. All right. So, whenever you have a differential equation, the thing that you end up solving for is usually the term that's in the time derivative. Okay. All right. Any questions on how we got to this point here? Okay. All right. So for this case, I don't have a MATLAB code for this just because this is just a single differential equation. And so we can solve this one by hand. Okay. If you need kind of a refresher from 308 or through 250B, this is an inhomogeneous first order differential equation. And so these equations we can solve using integrating factor. Okay. I won't subject you to the torture of going through an integrating factor problem, but it's definitely good. It's definitely useful to know. Even though we're going to be using MATLAB for the most part to solve our differential equation, it's just a good skill to know in general to know integrating factor. Okay. And so if we do that, we end up with the following. Right. And so our solution here for P of t is equal to e to the minus t over RC integral from 0 to t of q of tau I'm using tau as just a dummy variable here. That's the variable that we're integrating over. Okay. Q of tau over C times E to the tau over RC d tau plus E of 0, which is the initial pressure on the capacitor. All right. So again, I didn't pull this solution out of my butt, although it seems like it, this is the solution you get from using integrated factor. Okay. All right, so P of 0 here, this is the initial pressure on the capacitor. Okay. And notice how this is a generic solution because we're not given a form for Q of t. And so no matter what your Q of t function is, whether it is a sine or a cosine or a polynomial or an exponential function for whatever reason, this solution will work with all of this. The only caveat, of course, is that you have to integrate it together with an exponential term, which may not be convenient or fun. Question, yes.
Is the initial pressure on the capacitor like the pressure on the vessel walls before it starts expanding?
Yeah. Yeah. So mathematically, it's just your initial condition, but physically, that's you can usually a lot of these simulations are started in diastole, and we'll see that for the final project too. So that's usually kind of the resting pressure or the diastolic pressure of the system. Yeah.
That's like right before you spiked up again.
Exactly. Yeah. Yeah. At least for the flow waveform that I have that we'll use for the final project, it starts right before contraction. Okay. All right. Any questions on this? Okay. All right. Let's do another example. This one's a little more complicated. We'll throw in an inductor at this time. And this is one that we'll solve with math. So there's a reason I have 308 as a prerequisite for this class. First of all, is to just understand differential equations, but also so that you don't use this stuff in 308. So you can't cheat in 308. Okay, so let's consider the following lump parameter model. Okay. So it's going to be the same as last time, but we're going to add an inductor as well. So we have flow that's coming in. We're going to have inductor here in front. Okay. This is going to lead to a split. Just like that. Okay. We have our resistance and capacitance once again in parallel. That's a very common kind of arrangement that you'll see, resistance and capacitors in parallel. And then in series with this entire arrangement is an inductor. Okay. All right. So just like before, we're going to label the pressure at this junction right here P1. Okay. So that's something that's going to come out of our equation. So the pressure at that inductance. Okay. Another thing that we're going to label here is QL. QL there is going to be the flow over the inductor. Okay. And then upstream, our upstream boundary condition is going to be different here. So instead of an inflow boundary condition, we're going to have an inlet pressure boundary condition. So this is going to be PI of T. Okay. Where PI of T is the inflow pressure. All right. So sometimes you'll see your inflow condition given as a flow rate, that's Q. Sometimes you'll see it given as a pressure P. Okay. And it really all depends on which element is connected to the inflow. So in this case, since we have an inductor that's connected to the inflow, that means in order for our equations to kind of work out, we need an inflow pressure. Okay. Otherwise, it kind of gets a little bit dicey in terms of how the mathematics work. Okay. All right. In this particular case, I do give you a value for PI of T. because we are going to solve this one numerically using MATLAB. And so pi of t in this case is going to be 20 sine of pi times t plus 100. Okay. All right, so let's also assume, that all the circuit values are given. So the values of L, R, and C are given or known. Okay. And so based on this information, let's derive the set of ODEs that govern this system. And then let's solve for its solution in MATLAB. Okay. All right, so we're going to follow the same methodology that we did last time, except we have the inductor here, so that's going to make things a bit more complicated, right? And the fact that we have one inductor and one capacitor here means that we're going to have two differential equations that we can solve for simultaneously. Okay, because remember, that's always the first step whenever you have an LPM problem, is to count the number of inductors and capacitors, and that's going to be the total number of ODEs that you're gonna have. So one for each inductor, one for each capacitor. Okay. All right. So since we have two ODEs, let's go from left to right. Okay, so let's start with the inductor. So the inductor here is kind of on its own a little bit, right? And so if we look back to our equation, right? If we think back to our equation on the inductor, we know that dq L dt is equal to 1 divided by the inductance, or 1 divided by L, multiplied by the upstream pressure minus the downstream pressure. Okay. Where if we have an inductor like this, okay, P upstream is on the left side and P downstream is on the right. And the flow goes across the resistor just like that, right? So we know that the time derivative of the flow across the resistor is equal to the difference in pressure divided by L, right? All right, and what we said last time is that this equation here represents the inertia of blood flow, due to mass, right? Because whenever you have a pressure difference, that's going to drive flow, but because of the inertia, there's going to be a delay in terms of how much flow that causes, and that's what this equation represents. Okay, so let's look at our circuit up here, and let's see if we can determine what the upstream pressure and the downstream pressure of the inductor is. Right? Okay, so the upstream pressure, pretty easy to determine here. And so the upstream pressure, we kind of follow this wire here, is Pi of t. Okay, so P up, people do, Pi of t. We can just plug that into the equation. And then P down, right? Since we have a capacitor there, we know that we're going to end up solving for the pressure on the capacitor, which is P1, okay? So we have everything that we need to for the equation on the capacitor here, or the inductor, sorry. Okay. So know that dql dt is equal to 1 divided by L, Pi of t minus P1. Okay. If you wanted to at this point, you could plug in for pi of t, since we know the expression for that, right? We can plug in dql of t, dql dt is equal to 1 over L. We plug in for pi of t, this is 20 sine pi t plus 100 minus P1. All right, so that's the first equation that we have for this circuit. Inductors are pretty simple. So inductors, most of the time, you don't have to apply the circuit laws. You just apply the equation of the inductor just straight up. As long as you know the upstream pressure and the downstream pressure, it's pretty. All right. Any questions on this? Okay. All right. So next, let's do the capacitor. Okay. All right. And so luckily for us, this capacitor is in the exact same arrangement as our previous example, right? So we can apply conservation of mass here, or in other words, Kirchhoff's current law. So I'm going to go through it really quick. So let's go through this again, right? So we have our junction like this. Up top, we have flow over the resistor QR. On the bottom here, we have flow to the capacitor QC, right? We know what those equal. We know QR. The symbols are a little bit different here just because we're using different symbols, but this is going to be P1 over R, right? Because the back side of this resistor is connected to ground. And so, it's going to be P1 minus 0 divided by R. Okay? And we know that QC here, if we plug in the equation for the capacitor, is C times dP1 dt. Okay? And coming in, we have Q in. Okay? And so we can say that Q in is equal to QR plus QC. Okay. So Qn is equal to P1 divided by R plus C dP1 dt. All right, so pretty straightforward, right? So same as last time. The only mystery here is the Q in, right? The flow that's coming into this junction. Because it's a little bit different than last time. Because if you recall from the last example, for Q in, we were able to put in the inflow boundary condition Q of t, right? But our RC part here is not connected to the inflow, right? The inflow is connected to the inductor, right? And so the flow coming in, we don't know if it's a known quantity, right? But what we do know, and actually what we just wrote an equation for, is the flow over the inductor, right? And so, in this arrangement, because of conservation of mass, right, the flow that passes over the inductor has nowhere else to go except to go through the junction, right? Q in, this is exactly the same as the flow over the inductor. QL. Okay. All right, so let's go ahead and plug that in. And I'm gonna do the same thing that we did last time. Let me divide by C. Okay. Just to isolate, mostly just to isolate the pressure derivative. Okay. And another thing that I'm going to do here, just because we're going to need to input it into MATLAB this way, I'm going to subtract P1 divided by RC from both sides. Okay? Because what this is going to do is that this is going to isolate the derivative term by itself. on one side of the equation. Okay. And so we do all these things. So, there's three things we're doing here. We're plugging in QL for Qn. We're dividing the entire equation by C. And then once we do that, we're going to subtract P1 over RC from both sides just to isolate dP dt. Okay. And so if we do all those things, we get dP1 dt is equal to QL over C minus P1 divided by RC. So that's our second differential equation. Okay, so if we combine this together with our first equation up here, right? These two box equations are the differential equations that govern this non-parameter model. Okay. All right. Any questions on how we got to these two equations here? Okay. All right. And so now that we have these equations, the next step obviously is to solve them. Okay. And so you may look at a situation like this and say that, okay, we've already solved one differential equation, and we did it by integrating factor, or it's more like, Dr. Tran did it by integrating factor, and we just watched. But and so you're looking at these two equations here, and you think, okay, let's just do the same thing twice. Right? So solving one ODE by itself is it's a little tedious, but it's fine at the end of the day. We can do it. And so if we have two equations, we should just be able to do it twice. Well, the problem with this is that these aren't independent equations. In fact, these two equations are what we call coupled equations. And what coupled basically means that the solution of one equation depends on the solution of the other equation and vice versa. Okay. So we can't solve one without the other, and vice versa. So the only way to solve a coupled system of differential equations is to solve the entire system simultaneously. Okay. There's methods to do this. There's methods for solving a system of ordinary differential equations. Honestly, they're not that difficult. It's just that for the math courses that you guys take, they're very impacted. We have a lot of stuff we need to cover. So a lot of times, I would be surprised if either Math 250B or 308, we had time to kind of go over solving systems of differential equations, because practically speaking, they don't occur all that often. This is kind of one of the few cases where we see this. And so to kind of get around this difficulty here, we can solve these equations in math. Okay. Because MATLAB actually has a lot of tools for solving these kinds of equations. Okay. All right, and so I know, when I say MATLAB, it's a little bit, there's some anxiety that kind of comes with it. We're not actually programming in MATLAB, we're using a specific tool to help us solve these differential equations. And that specific tool is called ODE 45. All right. And so what we're going to do is, for the rest of class today is I have a couple codes where I show you how to use this ODE 45 tool. And once you kind of get used to it, once you kind of understand how it works, it's really nice. And you can use it to solve a lot of these kinds of systems. And it actually scales up remarkably well too. And so you can have a system of, I've seen it solve a system of 30 equations and 30 unknowns, all differential equations in ODE 45, and it's able to do that just like that.
Is it specific to a couple differentials or just any?
You can solve for any, and so even for single variable differential equations, you can solve it too. You can even solve it. So the way it's set up, you'll see in a second, it's designed just for first order differential equations, but you can even solve second order and third order equations too. Because if you have, a second order equation, this is just trivia. So let's say we have dp squared, d squared dp dt squared plus, omega p is equal to q of t, right? So a very classic second order equation. You can kind of decompose this into a system of first order equations. And so what you can say is that P1 or P2 is equal to d P1 dt. And then what you can say is that equation up there is equal to dp2 dt plus omega p1 is equal to q of t, right? And so for a second order equation, you decompose into two first order equations. There's no reason I'm showing you this. We're not doing second order equations, but I just think ODE 45 is super cool, and you can do stuff like this. So yeah, don't worry about that. We're not doing second order equations, but in case you were interested in exploring ODE 45 more, it's there. Okay. But before we jump into MATLAB, if my eraser would just speed up a little bit. Come on. All right, whatever. Let me write down our two differential equations here one more time, just so that it's just that we can kind of jump right into it. So we have dql dt. This is the differential equation on the inductor is equal to 1 over L times 20 sine of pi t plus 100 minus P1. And then we have dP1 dt is equal to 1 over C times QL minus P1 over R. Okay. All right, so these are our two differential equations. So we're going to see how to solve this in ODE 45. All right, any questions on this before we jump to MATLAB? Okay, all right, so let's go ahead and jump to MATLAB. So I've posted all these scripts on Canvas, and so they're available to you on Canvas, right? So I have MATLAB scripts for this example, and then I have one more example after this that I have the MATLAB scripts for as well. Okay. And so if you go to our Canvas site here, you go to week 6. Okay. On the bottom here, you can see that I have 4 codes here, but the codes kind of come in pairs. And so we have LPN example 1, LRC, and example ODE func. Okay. So this is the first example. These are the 2 codes that we're going to look at now. And then the other example that we're going to have, that's the one we're going to do next week, is example 2 LRRC.m and example ODE func 2. So we're just going to look at the first 2 files here. Okay. In fact, let me kind of close the other 2. This one's okay. I think it's this one. Yeah, we don't need this one. And we don't need this one. Yeah. Okay. So let's look at these two codes here. So let's start with we'll start with example ODE or example 1 LRC, okay? So the thing about these codes is that you have to kind of run them in pairs, right? And so one code is going to one code here is going to define the equations that govern your system, and the other code is going to run ODE 45. Okay. Okay, so let's go over the code for running ODE 45 first. And so that's what this code here represents. So if you open up this code, you can see I have comments here that kind of explain what each line of code does. Okay. And so the first line of code here is to specify the beginning and ending times that we want to solve for, right? And so for this first line of code here, we're defining a vector called time period. And so this tells us that we're going to solve this system for 5 seconds. Okay. And so this is basically telling the simulation to start at time is equal to 0, and then we're going to end at time is equal to 5. Okay. And so we're just basically setting the starting time. For the most part, your starting time is going to be 0. There's going to be very few cases where your starting condition is not going to be 0. And then your ending condition is going to be 5. Okay. Okay, next thing we're going to specify are the initial conditions for each of your solution variables. And so for this particular problem, our solution variables are QL, which is the flow on the inductor, and P1, which is the pressure on the capacitor. Okay. And so what we're saying here is that QL is equal to 60 milliliters per second. Okay. That's just the initial value for the flow, and P1, the initial value here is 100 millimeters of mercury. Okay. All right, so you're probably wondering, how did I get these units? You know, we didn't have any units given to us in the problem. The units are determined by the values of the circuit parameters. Right? And so the only thing that has units so far in our equations mostly are just the parameters, right? And so you can change the units of the parameters to give the solution in the units that you want. Okay. Okay. So once we define these two things, we're going to call the ODE 45 function. And so this is where ODE 45 is defined. Okay. And the way to use it is like this. And so if you've ever used the function in MATLAB, you know that you need to set it on the right side of an equal sign, right? So what we're saying is that t and y here, or t comma y, is equal to ODE 45. And then inside the parentheses here, we're given this, we call this an embedded function. I'll go over this part in a second here. Okay. Next thing that we give here is the time period. That's what we just defined up here. And the initial conditions for our parameters right here, right? Okay. So the way to kind of read this function is that, you know, whatever we have on the left side of the equal sign, these are going to be our outputs, okay? So t and y are the outputs of this function, okay? In particular, t here represents the time for our results, and y represents our solution variables. Okay. So the one here that's actually interesting here is y. Y here is going to be a vector, okay, that has two main entries. Okay. First entry will be our first solution variable, which in this case is Q underscore L. And second entry will be our second solution variable, which is P1, the pressure on the capacitor. Okay. I know I'm throwing a lot of information to you guys at once, and it's kind of hard to visualize unless we actually run it. But you know, I want to actually explain everything here first, and then we'll run it and we'll kind of analyze it all. Okay. Okay. And so the rest of the code here just plots, and so we'll get to that in a second. But I want to kind of focus on this first part here, which is just setting up the ODE 45 function. So to set up ODE 45, you have to define the time period, you have to define the initial conditions, and you have to feed it your equations function. Okay. Any questions on any of these parts right here? Okay. All right, so let's look at the other file now. So the other file is going to define our equations function here, example ODE func. Okay. Okay. So that's what this function is here. And so you're probably wondering at this point, where are our ODEs? And so, where's our equation for dq dt and where's our function for dp dt? Well, they're here. Okay. All right. And so in the other file here, you can see that it starts with the keyword function. So that's going to tell us that, we're defining a new function here in MATLAB, right? And you can see that it takes two arguments here. It takes t and y, right? Okay. And so if we want to find our equations here, our equations are down here. And so you can see that I've defined this new entry here, dy dt, okay? And it has two entries. And so the first entry here, this is our inductor equation. And so if you compare it to your notes, right, our inductor equation is 1 divided by the inductance multiplied by the inlet pressure minus the capacitor pressure, right? Or this inlet pressure Pi of t right here is given by this function here. Pi is equal to 20 times sine of pi t plus 100, okay? And then the second equation here, this is our capacitor equation. And if you compare this to our notes, this is exactly the same as our capacitor equation. So 1 divided by the capacitance multiplied by the flow rate into it, QL, minus the flow over the capacitor, which is P1 divided by R. Okay. All right, so the rest of the code here just defines what those values are. So we have Pi is equal to our inlet function, 20 times sine pi t plus 100. Here we specify the parameter values. We have the value of the inductance, the value of the capacitance, and the value of the resistance. Okay. Here I just kind of label the values here. So we have QL is equal to y of 1, right? So our first solution variable is QL, right? And then our second solution variable is P1. Okay. It's just that MATLAB doesn't understand QL and P1, and so it expects you to read in the variables through this y function right here. Okay. Okay. All right. So that was a lot of information. So let me just run it. So I think it'll make a bit more sense once I run it. Okay. And then after I run it, I'm going to plot the flow rate over the inductor as a function of time, and then the pressure on the capacitor as a function of time as well. Okay. All right. So let's go ahead and run it. All right, and so here are our results, right? And so you can see here that our results kind of look like a sine wave because our input was a sine wave as well, okay? All right, so you can see here that the flow on the inductor here starts at 60, and then as the flow changes, it kind of goes up and down just like that, okay? And same thing for the pressure on the capacitor. So the pressure on the capacitor starts at 100, and then it oscillates up and down according to the inlet condition. All right. So that was kind of a very fancy way, to solve kind of a coupled equation. But, the reason we're going through this is that when we have systems that have more than two equations, we can use the same framework to solve for all. Okay. All right. Any questions on that? Okay. All right, so this code is available to you online for you to play with, and so you can do different things. And so, you can see what happens when you change the initial conditions. And so let me just change this to 0 just to kind of show you what that looks like. Okay. Right. And so if you change it to 0, it's going to change some things. And so, definitely play around with these. Definitely get familiar with how to run these different functions, right? So I know I gave you kind of a really crash course here, but it would definitely be good to know these things, especially for the homework that's coming up as well. Okay.
Is the sine function one that you'd actually use to represent like a cardiovascular?
it's pretty close. And so, you know, the flow waveform and the pressure waveforms aren't exactly sine waves. So what I did here was kind of an offset sine. So you can see it.
showed, you could see the slight offset between the.
Exactly.
pressure and the.
Well, for this one, I offset it by 100 because normally a sine wave will go negative, and usually we don't have any big negative parts. And so I added 100 just to make sure it's all positive.
Yes, so you never hit 0.
Exactly. Yeah. So it's close, but it's not quite the exact one. So I have a closer I have a waveform that's much closer to this, but it's not a MATLAB form, so it's going to be for some. This one does a pretty decent job. It's not bad. All right, so if there's no more questions, we'll go ahead and end a bit early today, just because I don't want to get into the next example yet. So remember to finish up your SimVascular tutorial by tomorrow night. Make sure you submit it. If you have any questions on it, definitely let me know. Send me an email, and we can take a look. Right. Next week's gonna be a bit busy because we're gonna have you guys select your model for your final project, and then you're working on this homework here. So definitely get used to it. All right, so thank you guys for coming today. Hope you guys enjoy your weekend. Hope you guys enjoy the rest of your day, and I will see you guys next week.
I've got changed to I'm ready to go see graduation. Yeah, how do you change it to?
I'm down to do it if like we all.
Graduation stuff.
I'm pretty sure we approved all this.
Yeah,
Go ahead and send me an email. I'll double check the file. Yeah. Go ahead and send me an email just to remind me. I'll check when I get back to my.
I did like rest. I don't know. I say one time. I wish I could so bad. I agree with you.
You think they've been a little, you right, but that's.
The person behind us.
Hey, man.
I gave one guy. I gave him the. Yeah, bro, 'cause I gave him the junior my freaking now. The junior? I gave Avery. I asked Avery if she could work on David's part.
I think she's the only junior we have.
No, she didn't. She didn't really try that.
Tried that out a couple of weeks ago.
Who else would it be on?
Rex.
That's crazy.
She really wants this too.
That's crazy.
And she can do it.
That's crazy.
That would be OP.
She literally.
How did you?
Not
like how she is now.
Yeah, exactly.
Oh, really? She was like doing something earlier? Then how she?